In this video, we are talking about the different characteristics between salt water and pure water. And by doing so, we're going to be using boiling point, melting point, freezing point, and also vapor pressure. So let's begin with our boiling point.
So right now, we're going to look at the boiling points of salt water and regular water. In the silver pot, we have regular water, and in the black pot, we have salt water. And as you can see, they're both at a medium temperature, and the water is straight from the tap, so nothing changed. So we're going to look at the different boiling points and see which one boils faster, the regular water or the salt water. So as you can see now, the plain water is now having a full boil, and the salt water, it's still getting there. So right now I'm gonna give each of these 2 minutes, and we're gonna see how the egg cooked.
So before we look at the eggs, let's look at the water. As you saw, the water in the silver pot boiled faster than the salt water in the black pot. And that is because the salt increased the water's boiling point. Now this happens through boiling point elevation, which occurs when a non-volatile solute, such as salt, is added to the solvent to raise its boiling point. Now, the new saltwater solution needs more heat to start boiling than the pure water does. So it takes time to boil. So you really have hotter water, but it's not boiled faster.
So we look at the eggs that were in the solvents. This is the freshwater egg or the pure water egg. And as you see, it cooked fairly, and it looks good enough to eat. But if we look at the saltwater egg, it still kind of looks, not fully cooked compared to the freshwater egg. So as you see, even though the salt water required higher heat, it also required longer time. So if we would have left the egg in for let's say 2 more minutes, I feel it would have been fully cooked compared to the freshwater egg. So we're going to be talking about the vapor pressure of salt water and pure water. And I have the same containers that will help not change the variables. But before we get into the demonstration, let's talk about vapor pressure of solutions. Now, the vapor pressure of a liquid is much different in a solution than it is in a pure liquid. The dissolved non-volatile solute, which is the salt, lowers the vapor pressure of the solvent, which is the water, as you see. The solute decreases the number of solvent molecules per unit volume, lowering the tendencies for the molecule to escape into vapors. So what it's trying to say is, since salt is inside the water, it's going to have a lower vapor pressure, which means that there won't be as much vapors condensing on the top compared to the pure liquid. So let's get into the demonstration. I pour the water into the containers. So I'm going to close and wait for a good minute or 45 seconds. And we're going to take the tops off and look at the vapor. So as you can see, this is the salt water and this is the pure water. And looking at the pure water, you can obviously see more molecules were able to leave the solution and go up to the top of the lid compared to the salt water. And that's mainly because of the salt, and it lowered the pressure, which means more salt molecules and a little bit of water molecules are actually trapped inside the solute, which means that they're not able to escape onto the lid and be as present compared to the fresh pure water. Right now we're going to be focusing on the melting points between salt water and pure water. So right now these ice cubes are made of pure water, but we are going to pour some salt onto we're going to pour some salt onto this side, the left side. So now we're going to watch and observe. This might take a while, so I'll come back and show you. So as you can see, the ice has melted, and from the looks of it, it looks like the ice with the salt on it melted faster. So let's remove the ice. But you kind of see how this one is kind of smooth, and it really doesn't, you know. But then if you look at this one, the salt is really hard on it. And like you can kind of see the grooves of where, you know, especially on this side where the salt melted the ice. But looking at the puddles they made, the pure water really doesn't seem like that much. But the salt water here, you can tell that the puddle is really, you know, big. And all in all, in a real big nutshell, the salt is a great ice melter because of something called the freezing point depression. And really, that focuses mainly on ice being melted by the salt. And this means that the salt helps lower the freezing point and consequently the melting point of water. In its pure state, water freezes at 0 Celsius or as 32 Fahrenheit. By using salt, that freezing point can be lowered, which forces the ice to melt and prevent the water from freezing or refreezing. So that is why when it snows, you see salt on the side of the road, because when you pour salt into frozen roads, the salt dissolves into liquid water in the ice and lowers its freezing point so that the temperatures have to get even colder to make the salty water freeze again. The tray to the right has regular tap water and the tray to the left has salt water. The tray has the same volume capacity and we're using the same temperature of water so it doesn't affect the outcome. So I'm going to put both of these trays in the freezer for 2 hours and we're going to see the result. You can see I took the water out of the freezer and this is the pure water and this is the salt water. Now I already tried poking holes in them and to see if they, you know, froze. And the salt water didn't freeze all the way, as you can see. But the pure water froze solidly. And this is because pure water freezes when water molecules of hydrogen-oxygen bonds come together to form a crystallized ice structure, as you see right here. But when salt is added, it is more difficult for the molecules to bond. So that means salt water has such a low freezing temperature. That's, as you see right here, it's literally, oops. And the greater the salt levels, it means the lower the freezing point gets. As in, it's going to take a lot of, it's going to take a lower temperature to freeze this fully to make it become this. You see my presentation over there? Mm-hmm. Yep. Now come see. How does, you see how I froze this for 2 hours, as you can see, right? And in 2 hours, this is salt water, this is regular pure water. And you see how fully this, you know, solidified?
Formed, yeah.
Yes. This one was not as, you know,
solid.
formed. Yeah, it's not as solid. And you can kind of see, because what you see here is really the water that is frozen, but not the salt.
All right, cool.